Welcome to section 4.7. So far, all of the second order differential equations we have solved have had constant coefficients. Today, we're going to look at a way to find a fundamental set if the coefficients are variable in two special cases. One is that we already are given one solution, a y1, and the other is if it's a very special type of differential equation called equidimensional or Cauchy-Euler. So let's look at the reduction of order formula first. This is the way to find a fundamental set if you're already given one solution. So the first thing, the differential equation has to be in this form, meaning the coefficient of y double prime has to be 1. It has to be a monic differential equation. Once you've identified p of t, which is the coefficient of y prime, compute the term e to the negative integral of p dt. Then the formula for your y2 is given right here. Don't memorize this. I'll give it to you if you need it. You just won't use it often enough to memorize. So let's look at examples. Given y1 is a solution of the dE, y1 is t, find a second linearly independent solution, assume that t is greater than 0. So first thing we have to do is put it in the correct form to determine p of t. So divide through by t squared, y double prime minus 1 over t y prime plus 1 over t squared y equals 0. So p of t is negative 1 over t. Okay, so we want to compute e to the negative integral of p dt, which is e to the integral of 1 over t dt, which is e to the ln absolute t, which is t, since we're given that t is greater than 0. Okay, and then 2, we're going to use the formula y2 equals y1, I'm using this formula up here, y1, which is t, integral of e to the negative p integral of p dt. We just computed that in step 1, so there's a t that goes upstairs, and then a y1 squared goes downstairs. y1 is t, so t squared dt, which is t integral of 1 over t, which is t ln absolute t, but t is positive, so t ln t. And we'll see there's another way to get the same answer later on in the lecture. Moving on, Cauchy-Euler. All right, so how does this method work? First of all, it only works for certain types of equations, and those are called Cauchy-Euler equations. So what's special about Cauchy-Euler is the coefficients can be variable, but the power of t has to match the order of the derivative. So here I've got 4t squared y double prime, 4t squared y double prime. So y double prime gets paired with t squared, and then there's 0 t y prime. So this is t to the 1, that's first derivative, and then 17 t to the 0 power of t, and then y, the y is considered the 0 derivative of y, and that equals 0. So that's Cauchy-Euler. This one doesn't look it at first, but if you multiply by the whole thing through by t squared, then it looks Cauchy-Euler. T squared y double prime minus t y prime plus 1 times y equals t squared e to the t. So t squared, t, no t. Okay, if you have a Cauchy-Euler equation, here's how you solve it. The characteristic equation is a little different than it is for a constant coefficient equation. It's ar squared plus b minus a times r plus c equals 0. And there are 3 cases. It's a quadratic equation, so 3 cases. Just want to point out, before, when we were solving a y double prime plus by prime plus cy equals 0, and we had solutions that looked like e to the rt, where r was a solution of the characteristic equation. Now we have a different characteristic equation, and our solutions don't look like e to the rt, they look like t to the r. And then for the constant coefficient case, if we had a repeat root, we had e to the rt, and then we multiplied by t, like t e to the rt. Here, if you have a repeat root, you multiply by ln t. And then the complex case looks a bit funky, but it comes about from Euler's formula, so it's not hard to prove, and I did it at the end in the frequently asked questions. Okay, a couple remarks. Well, one remark, I just mentioned that I've got the proofs of these formulas at the end, and the other remark is using the EUT from section 4.2, part 1, solutions of Cauchy-Euler equations are only going to be valid on t positive or t negative, not at t equals 0, because you have to divide through by t squared. So we're going to assume in this section that t is positive. There's a way to deal with t negative, and I put an example at the end of the lecture notes, but we're going to assume that t is positive. Okay, so let's solve some Cauchy-Euler equations. First one, find the general solution of this differential equation. If I multiply through by t squared, I will quickly see that this is Cauchy-Euler. So it's Cauchy-Euler, and A is 1, B is -1, and C is 1. And so my characteristic equation is r squared plus b minus a, -1 minus 1 times r, plus c, which is 1, equals 0. So that's r squared minus 2r plus 1 is 0. So that's r minus 1 quantity squared is 0. So I have a repeat root of 1. So I go up to my little box and I see what to do in the case of a repeat root. I multiply by ln t. So my general solution is y equals c1 t to the r, which is just t to the 1, and then plus c2 t ln t. Okay, let's do another one. So this is already in the Cauchy-Euler format. A is 1, B is 3, and C is 5. So our characteristic equation is r squared plus b minus a, 3 minus 1 is 2, 2r plus 5 equals 0. Now that's not going to factor very easily, so we're going to use the quadratic formula. R is -2 plus or minus square root of -16 over 2a, which is 2, which is -2 plus or minus 4i over 2, which is -1 plus or minus 2i. So my alpha is -1 and my beta is 2, and I've got complex solutions. So y equals c1, sorry, my alpha is -1, right? c1 t to the -1 cosine of beta ln t, 2 ln t, plus c2 t to the -1 sine of 2 ln t. Okay, non-homogeneous Cauchy-Euler equations. So the general solution process is first to find the general solution of the homogeneous. So you're going to be using the Cauchy-Euler formulas on the previous page, and then use variation of parameters to find a YP. When you do that, first you need to put this into the form for variation of parameters, which is the leading coefficient has to be 1. So before you identify your f of t, make sure you divide through by t squared if you need to, which I did. Okay, so let's get started. I'm going to find a general solution of the homogeneous. So my characteristic equation is r squared minus 2r plus 1 equals 0. We actually just solved this. This is r minus 1 squared is 0. So I have a repeat root of 1. So yc is c1 t plus c2 t ln t. So when I do variation of parameters, I need my y1 and my y2. I'm going to let y1 be t, and I'm going to let y2 be t ln t. And f is not, here's my original differential equation, f is not 2t, because first you have to divide through by t squared. So f is 2 over t. All right, and now we need our w. So w is the Wronskian. T and t ln t go on the top. 1, and then the derivative of this, I have to use the product rule, ln t plus 1. So that's t ln t plus t minus t ln t, which is t. So my Wronskian is t. Here we go. V1, I'll remind you of the formula. V1 is the integral of -y2f over w dt, which is the integral of negative. Y2 is t ln t, f is 2 over t, w is t. So that's the integral of -2 ln t over t dt. So this is a u sub. U is ln t, du is 1 over t dt. So this is the integral of -2u du which is negative u squared. So negative, and u squared, I'm just going to back substitute. U is ln t, so that's negative ln squared t. I can write it like that, kind of like a trig function. And v2 is the integral. The formula is y1 f over w. y1 is t ln t, f is 2 over t, and w is t. Sorry, screwed up, huh? y1 is t. So this should just be t. So that's kind of nice because then we end up with the integral of 2 over t, which is a lot easier, which is 2 ln absolute t. But remember, with Cauchy-Euler, we're assuming t is positive. So 2 ln t. Then yp is v1 y1 plus v2 y2. Okay, v1 was negative ln squared t. y1 was t. And then plus v2, which is 2 ln t, times y2, which is t ln t. So this is, I'm going to put this t in front, negative t ln squared t plus, we've got an ln t times an ln t, and I'm going to take this t and put it after the 2 ln squared t. So I end up with a single t ln squared t. All right, and that is the end of this lecture.